What I want to do here is a really cool thing. This whole stuff is cool though, but this is where we're going to calculate the ground state energy for hydrogen and the radius of the electron. This is just from high school physics, and it's amazing stuff. This is what Bohr did, and his whole idea was, and from this you can calculate all those energy lines in the hydrogen spectrum. His whole idea was that, you know, we've got this quantization thing where Planck said that energy of the oscillators was quantized. You know, we're saying, Einstein's saying E equals hf, the energy of the photon's quantized. And he's saying, hey, maybe the energy of the electron is quantized, and that means that it just comes in discrete packets as the angular momentum we're talking about. So let's go with mvr equals n h dash, Planck's constant. N being, hey, if it's quantized, it comes in discrete units. N could equal 1 or 2 or 3, and the ground state n would equal 1. So this is just our angular momentum formula for a little mass operating at a distance. So that's the radius. This must be the radius at which the electron on the hydrogen is orbiting in that model we've got. So we've got a little formula there where we can just bring down the m and the r, and we've got a formula for velocity now. Now, h with a slash through it is just h divided by 2 pi. So that just comes out of the maths. There's a bit more complicated stuff we can do that we won't do, that will show you where that comes from. But anyway, let's do the whole centripetal force, centripetal acceleration times the mass, must be being provided by Coulomb's force law of attraction between two charges. One of the things that we sort of miss out in high school, but it's pretty simple. It's just like the gravitational force law. So if we do that, we can then get rid of that r, get rid of that, and we can actually say, oh, okay, if I just divide both sides by 2, then I've got a formula for the kinetic energy, right, the electron, right, which is ke squared over 2r. Now, we did talk about this. If you want to know the potential energy, so you've got this little proton, you've got this electron, if you take it away to infinity, and you're taking it against the force, it's gaining potential energy. At infinity, it's going to have 0. We define infinity as 0, so all these little potential energies in between must be negative. Okay, it's still positive changes in energy, but we define it that. So the potential energy on the electron is going to be a negative thing. We just define the kinetic energy as a positive thing. But if we do that integral, where we actually basically just do force times distance to calculate that energy, the only thing is the force keeps changing as the distance the electron gets away from the positive charge gets bigger, so it becomes an integral, but it's quite a simple integral to do. But if we do that, we find that the potential energy of the electron at that point is going to be equal to minus, as we just said, kq squared over r. Right? So total energy is just kinetic energy plus potential energy, these two little guys, ke squared over 2r minus kq squared over r. That's just a half of that one, but that one's negative, so that's like minus 1.5. Minus 1.5 is minus a half, right? So the total energy must be minus ke squared over 2r. That's the total energy. So we're looking good right now. What we now need to do is go, okay, we've got this formula for V, all right? So we go back to our formula up there, which was mv squared over r equals Coulomb's law, ke squared over, let's just see, r squared. So that was the one we had there. And what we can do is we can go, cut that one out, bring the m down here, right? And cut that out. So we've now got v squared ke squared over rm, right? And what we can do now is substitute for the v squared. We have a formula for v here, which says v equals n h slash over mr. So v squared is just all those squared. So we can say basically that these two are going to be equal to n squared h slash squared all over m squared r squared. So we can say those two are equal. Let's just simplify this all down, and what we're looking for is just something to tell us the radius that that electron's at. So I think what we need to do is bring our r's up here, and so we end up with an r up there, that one having cancelled, so boom, boom, that one's gone. We can cancel the m on that side, so we've got n squared h slash squared on the top there. We've still got an m on the bottom, and we've got a ke squared, right? And that should be our formula for r. Now, if we plug in all the numbers, which we can, we're going to end up with a number that basically says 0.0529 nanometers. So pretty small, but we've got a radius. It's really cool. And we did that just by equating the, well, using fundamentally Bohr's idea. And the centripetal force. What I want to do now, though, now we've got that, let's see what we can do with working out the total energy. Because now we've got a radius, we can go back to our total energy formula, which was just here. E total equals minus ke squared over 2r. If we put that in and solve for it, because we've got our r here, we can put it in there, we can solve, we will get it equaling 13.6 electron volts. Negative, of course. I told you why they were negative. Pretty cool. We've worked out the radius and the energy of the ground state of hydrogen. Now, if we substitute in our r into our ET formula, then we've got a formula for ET, which doesn't include r. We're going to end up with minus, because it is a minus, ke squared m ke squared all over 2 n squared h slash squared. Now the reason I wanted to do that was because look what we've got there, n squared. So basically, and for a 13.6 volts our energy was for n1. So if I want the second level of energy, so we could call for n equals 1 equals minus 13.6 electron volts. For n equals 2, it's just going to be minus 13.6 electron volts divided by 2 squared. N equals 3 is just going to be equal to minus 13.6 electron volts divided by 9. I think you're starting to get the idea of what goes on with this. Now, what you will see, you won't necessarily see formulas like that in your homework or your notes, because what they do is they go back to old Rydberg's constant, and that's the one you'll see. So we can get an ET that is actually equal to minus HC R, big R, that's Rydberg's constant, all over n squared. So basically what you can say is that must be equal to minus 13.6 electron volts. But when you do it like that, and just use Rydberg's constant that he worked out just by trial and error, it's pretty meaningless physics. You know, this we showed how we got it, and we got it by using Bohr's principle of quantization of angular momentum and simple mechanics. All right, so that was a pretty cool thing to do.